So the Lagrangian is the following. So you have the complex scalar field here, okay, the big phi. So you have to take the complex conjugate of the first guy, and then you have the mass term for this, m squared, phi squared, and then you could have the potentials. Well, I use mu, and then the other term is minus lambda. Okay, so you have the parameter which is mu and the lambda here. Okay, so in this complex scalar field, you have 2 degrees of freedom. Okay, one is like a real part of the of this phi, and then the other is the imaginary part of this scalar field. Okay, so when you have the U1 symmetry, it means you have this symmetry of U1 rotation like this. Okay, so it's just the rotation with alpha now is just a constant, it's just a phase. So when you do this transformation, the Lagrangian remains invariant under this transformation. Okay. So in this case, we are going to break the symmetry, and what we are going to see is that there is a non-trivial vacuum for the scalar field. Okay, and so the first thing that we are going to find is we are going to find the minima of this potential. Okay, so this is like a minus potential, and the potential is a function of the amplitude of scalar field, like this. Okay, so V is minus mu. Oh, yeah, should look for this, and then plus lambda. And to find the minima, you just have to take the derivative with respect to the field, right? And then set it equal to 0, and then you find that. But I will use another notations of this complex scalar field. So let me use this notation. I will introduce this like a. You can write down this complex scalar field as rho times e to the I pi. Okay, so rho and pi is a function of x. Like this. So basically, I'm just writing down this complex scalar field as in the polar form. Yeah, nothing deep. Right. So in this case, you see that the pi here has dimension 0 since it's in the exponential. Okay, pi has dimension 0, and rho here has dimension 1, the same as the dimension of the complex scalar field. In energy, of course, and then you plug this polar form back into this potential, so you get, of course, when the complex conjugate of this gives you e to the minus pi, and then pi is going to be disappearing from this potential, and what you have is just a function of rho. So it's just minus mu square rho squared plus lambda rho to the fourth. Okay, and of course you can write out, and you can just factorize this rho square, and you get mu square minus lambda squared. Okay, and then what you have to do is you have to take derivative of this potential with respect to rho, the radial field, and then set it equal to 0, and then you obtain the minima of this potential. Okay. It's pretty easy. Okay, so let me look at the note, because otherwise I will do some mistake. Right, and then you take a derivative, you get the following: dv d rho. Okay, let me take a derivative. Rho plus 4 lambda rho cube. Of course, you set it to 0, and then it's a cubic equation. It has 3 roots, and then the roots are the following. Okay. So you get rho 0. Okay, so now there are three rules. One is the sitting at rho 0 equal to 0, rho equal to 0, and the other two are sitting at mu divided by square root lambda. Okay, so what happened is that when you draw this potential as a function of rho, what you have is this for the potential. Okay. Okay. So here is a maximum, and then you have two minima here. This is rho, let's say minus mu divided by 2 lambda, and this is plus mu divided by 2 lambda. Okay. So you're seeing that when you sit on top of this potential, the U1 symmetry is still there. But then if you choose the non-trivial vacuum, which is either this or this, what you are going to have is that this U1 symmetry has been spontaneously broken. Okay, so what I mean is that when you choose the non-trivial vacuum, you choose rho 0, which is different from 0. What happened is that when you transform the U1 symmetry, like e to the alpha, and then acting on rho 0 or phi 0, this is going to be different from 0. So the vacuum now carries some non-trivial charge under the U1, carry non-trivial U1 charge. Okay, and now we see that once you are on this vacuum, the U1 symmetry has been spontaneously broken. Okay, right. In this case, yeah, of course, the U1 is a global. It's a global U1. And once you choose this non-trivial background, you break essentially from U1 to nothing. To break the full rotation to nothing. To nothing. And when you count the degree of freedoms before and after you break a symmetry, before you break a symmetry, you have the complex scalar field. It has 2 degrees of freedom, because it's a 2 complex scalar field in this case. And then once you break, this number of the degree of freedom should be preserved. So it should be the same. So it should be the same. And now we would like to see how this 2 degrees of freedom after you break a symmetry appears. Okay. So now suppose you choose this rho, which is mu over divide square root lambda, and we want to do some perturbation around this vacuum. Okay, and then we see that there are going to be 2 directions. One is a radial direction that acquires some mass, and the other is angular directions that is the massless degree of freedom. Okay, right. Okay, let me go on. But if you notice, I intentionally put the plus sign here because when you sit on top of the potential, it seems to be that you have a tachyonic instability, but it just means that you are you should choose another vacuum, and you should expand your do the expansion perturbation theory around this new vacuum. Okay, it seems to be that you have a tachyonic instability here. But the same story goes when you have like a K-essence theory, P of X. In that case, you would have ghost more or less like a ghost instability, like what you call ghost condensate. And then you have to choose another vacuum for P of X. And there, the same story goes for that. Let me try to choose this vacuum and then expand around the field around this vacuum. Okay, and see that you're gonna have explicit Lagrangian for the Higgs and the Goldstone boson. Okay. Okay. Right. So what happened is that now we want to do this kind of expansion. We choose this, and this is like a real part of phi, and this is the imaginary part of phi. And now basically we have a circle, have a circle. And here there are two directions. One is the radial direction, and the other is the angular direction, like this. Radial direction, yeah. Okay. So let me call it the field in the radial direction as H, which is Higgs essentially. And then the other field in the angular direction as a pi field. Okay. So this is a rho 0 point. Rho 0 is your non-trivial vacuum that you have. And then around this rho 0, let me expand the field around this. So it's 1/2. Yeah, let me call it rho 0 is V divided by square root 2. And then V plus H e to the I pi. Okay. So now what we are doing is we are expanding around this non-trivial background with some radial field, and then we have some angular directions field, okay, pi. And then what we are going to do is we plug this back into our Lagrangian and see what happens. Okay. So you can go on and do the computation as an exercise. Okay. That you use this plug it back here. Okay, so plug it back here. What you get is the following. You are going to get the Lagrangian for two fields. One is H, and the other guy is pi. Okay. Remember, pi has dimension 0. Huh? It's a bit weird, but who cares? Okay. Okay, so after we plug this form back into this Lagrangian, what we get is the following. Okay, so let me just write down this Lagrangian. H. Okay, so this is the Lagrangian after you plug this form back into this Lagrangian of the complex scalar field. Okay, so what you have is that first you have the massive scalar field. Okay, this H is a massive scalar field, which is called Higgs. Okay, so you have Higgs mh squared, which is mu squared. Yeah, let me just mu. Yeah, it's just mu squared. And this mu square is lambda times v squared. Okay. Yes. This lambda is coming from the lambda of this lambda. Okay. And v here is a vacuum of the scalar field. Okay. Right. So now you have the mass of the Higgs, and this is a Higgs mass. And in addition to this massive mode, you also have the massless mode, which is this pi. Okay, so this pi plays a role of the Goldstone boson. Goldstone boson. Because if you expand this, it's going to you have v square plus 2vh plus h square. So yeah, basically you don't have a mass term for this pi guy, but you have instead you have interaction between h and pi, something like h d mu pi square and h square d mu pi square. Something like a cubic interaction between h and sorry, 1h and 2 pi. Okay, 2 pi and 1h, and then quartic interaction. Like this. Okay. So now you see that after you break a symmetry, the degree of freedom is preserved. That before you have one complex scalar field, corresponding to real and imaginary. So you have 2 degrees of freedoms. And after you break the symmetry, you have 2 scalar fields, one massive and one is massless. Okay, so you have one massive and one massless. Okay. Okay, so you see that this number remain the same. Okay. So far we have not gone to the EFT yet. So it's just writing down the complex Lagrangian around this non-trivial background. We just break the symmetry. But then after this, we are going to integrate our H. Okay. So far we are still in the UV 2 fields, like a 2 field models. If you want, like you have one field is H and the other field is pi. Okay. And the next step would be to integrate out the massive field H. Okay. When the energy scale is much less than, or it's less than the mass of the Higgs.
The mass in front of the H squared is
yeah.
So it's opposite side.
Opposite side, yeah. Yeah. Actually, if you put this to be negative, you will not be able to generate that kind of potential, and the Mexican hat potential. Yeah. Well, it depends on the sign of the mu square as well. If you put this minus sign and then you allow for mu square to be negative, and that's some sort of like a tachyonic like instability thing. But it's not really instability. It's just that you have to choose another vacuum, like this rho 0. Yeah. If you are still sitting on the top of the potential, you may think, yeah, it's kind of a tachyonic instability. Yep. Anyway, so now we have 2 field models, and then what we are going to do next is the same story as what we did before for the 2 field models, to integrate out the heavy guy here and to get the IR Lagrangian for the pi field. Okay, because now pi is a masses, so then it makes sense to integrate out the radial mode or the Higgs fields. Okay. And as a result, as a spoiler to the story, you get the K essence. Okay. So in this sense, we can say that the K essence can be UV completed into this U1 complex scalar field. Okay. Okay, let me do it. Okay. So now we are going to integrate out the Higgs. Integrate out the Higgs. Okay, so for simplicity, we just focus on the 3 level. That means you can use the equation of motion of the radial guy or the Higgs, and you can just write down the equation of motion of this guy, and it's the following. By the way, I forgot to say that to answer your question in the morning session, the non-linearly realized. So if you stare at this Lagrangian, the symmetry of this, of course, it's not the U1 because U1 has been broken, but the symmetry that you can realize is this one. Pi goes to pi plus C. So it's just cheap symmetry. Why? Because pi always appears with a derivative. So now you have cheap symmetry from here. Okay. So yeah, this kind of this cheap symmetry is a kind of it's a nonlinear kind of transformation because it's a kind of translation like this. So if you have a linear transformation, it's more like a rotation thing. You know? Okay. So yeah. So now yeah, we have this cheap symmetry in the EFT. Sorry, in the broken phase. In the broken phase. Yeah, so instead of U1, you have this cheap symmetry of pi. Okay, so you shift this and derivative kill this constant. But of course, H doesn't have cheap symmetry because of this potential. Of course, when you shift H, this gonna be changing as well. Okay. Now, let me integrate out this H by writing down the equation of motion of H. It's the following. Get out H. Well, schematically, okay, because the I think the full example will be in my exercise in the tutorial. Okay, so if you write down this H plus mu, equation of motion H, and then you have mu H squared, and then you have maybe style, maybe it's not correct, but fine. And then for these, yeah, you can just perhaps for simplicity, we can just if you vary this respect to h, we are going to get the I pi, something like this. The I pi, and then if you vary with respect to h, you get this thing. There should be some factor here that I don't keep track of. Okay, but then the idea is that you can solve this equation. Okay, in terms of pi. Let's say that you can neglect this. Divided by v to the fourth. Okay, and pi c. Well, let me just. Pi c here is more like a canonically normalized field. Okay, so it's more like v times pi. Because you see from these that you have the first term is going to be like v squared the mu pi squared, and then you can normalize your pi here to go as pi c over v, like this, just to cancel this v squared here, and then you get that Lagrangian. Okay, and if you think, this is kind of because K essence is more like a theory of when you have the Lagrangian as a function of x, where x is a kinetic term, right? Like a d mu phi squared, right? So yeah, this kind of thing is just a function of d mu pi squared. So in the sense that this EFT or the IR the Lagrangian can be UV completed into this U1 complex scalar field. Okay. But I leave this kind of procedure to your exercise. Okay. And C1 is this C1 is mu squared divided by v to the fourth. Oh, sorry, v squared mu squared. Okay. Good. Right. Yeah. So now our discussion here is for the global U1 symmetry, and now we are going to gauge the this symmetry, in a sense that the gauge parameter alpha is now is a function of space and time. Okay. So this alpha that we had before, when you send phi to e to the I alpha phi. For the local case, you let this alpha to be a function of x, okay, x mu, essentially. And once you do this, you gauge this parameter. What happens is that you have to take into account the gauge field, okay, to preserve all the symmetries, to preserve this symmetry. Okay, and now we are going to do a kind of baby version of Higgs mechanism. The full version you do it for SU2 cross U1. It's a baby version of that. or U1 version, abelian gauge version, U1. Okay. So let me call this abelian Higgs model. So it's more like a Higgs mechanism, but for the U1 symmetries. Okay, but in this case, as I said, the Lagrangian has to be the one of like a scalar QED, if you want, like a scalar QED that you have. Yeah. So you still have the complex scalar field like this with the potential, and then with the potential. And then you have the part of the gate field on 4 F mu nu, like this. Okay, and so this d mu is a covalent derivative associated with the U1 gauge symmetry. The mu is a covalent derivative. You know the covalent derivative in GR, right? That is like with the Christoffel symbol and so on. But here we have the covalent derivative for the scalar for the one with the U1 gauge field. I.e. a mu phi like this. I hope it's a plus sign. Why E is okay. Okay. Right. And this is a covariant derivative. Covariant derivative. Yes. You can check that as an exercise, okay, as your exercise. You can check that the mu phi transform nicely under the U1, the local U1. So this guy is going to be transformed as e to the alpha as a function of x, and then the mu phi. Okay, under U1. Under U1, local U1. You can check this. And also, of course, we have the gauge invariance that when you shift a mu, so you also have the gauge invariant. Like d mu, in this case, it's going to be minus, d mu alpha over e, something like this. You can check that this Lagrangian is invariant under this gauge invariance, gauge transformation of a mu. Yep. Right. And now what we are going to do is that, of course, this part of the scalar field here, the potential has some non-trivial background as in the case of the global U1, and then in that case we can write down your complex scalar field in terms of rho, the radial mode and the angular mode. Okay. So, okay. Here now it's a local. Oh, it is. Okay. So yeah. So what happened here is that you can write down. Yeah, still you can write down this phi as a phi of x, rho times e to the I pi like this. And the same story goes. You can you have rho 0, and you expand your field around some non-trivial background, like around rho 0, which is the v divided by square root 2. Okay, but the point is that here we have the gauge. We have more freedom. We have the gauge invariance. It means that we can choose alpha to be any function we want. In this correspond to to fixing the gauge. Okay, so what I'm going to do is I'm going to fix the gauge or fix alpha to be equal to minus pi. Okay, in this case, when you fix alpha to be minus pi, the new pi is going to be 0, because after you do all these things, remember that the pi has this symmetry, pi plus alpha. Okay, and when you choose alpha to be minus pi, it means the new pi in the new frame pi is 0. Okay, so in this choice is called a unitary case. Okay. Unitary case. Okay, so now you in a sense, this unitary case means that you set the Goldstone boson to 0. Okay, you set Goldstone boson to 0, and because this is Goldstone boson. But when you set this guy to 0, it doesn't just disappears. What happened is that this guy will reappears inside a mu, and it becomes one of the a mu degree of freedom. Okay, so as a consequence, a mu becomes massive. Okay, before the a mu is a massless gate field, no. For the massless gate field, it has 2 degrees of freedoms. But once you choose this gauge, like a unitary gauge, the mu becomes manifestly massive. And for the massive gauge field, it has 3 degrees of freedoms. Okay, 3 degrees of freedoms. One is the longitudinal mode, and the other 2 is a transverse mode. Right. So it contains 1 longitudinal mode and 2 transverse mode. Okay, so we are going to set pi to 0, and then we are going to see that using this Lagrangian, we produce the massive gate field. Okay, let's right. So basically, when you choose pi to 0, this form of the scalar field just simply becomes v over 2 plus the Higgs. Okay, because e to the I pi is just 1, because you set pi to 0 already by choosing this gauge choice. And now this complex scalar field just simply become rho is v plus h. V over square root 2 is a vacuum, non-trivial vacuum. Okay, so you plug this back there, and okay, what you have at the end. Keep in mind that now we are around this non-trivial vacuum. Okay, oof. But this vacuum, let me just mention that this vacuum is a constant for now. For now, because for our cosmology that I have not touched upon yet, in cosmology this V becomes a time-dependent function. Okay, this is a constant for now. And it could be a function of t, of time, and or a function of space, whatever you want. Then it gives different symmetry breaking pattern. Okay. So now, after you using this and plug it back here, what you get is the following. Okay. So let me do term one by one. So this term, the kinetic term for the complex scalar field, give you the following. So it's like minus. Okay. So now you see that the kinetic term for the complex scalar field gives you the mass term for the gate field. Okay, so this a mu, and it's like a mass term for the gate field, and the mass of a mu is like g square v square. Okay, so now you have produced, you have generated the mass for the gate field. Originally, you start from the massless gate field, no? Because you have to respect the gauge invariance. But after you break a symmetry and choose the unitary gauge, and then you get this mass term for the gate field, and the gate field becomes massive, as I said. But of course, you can work in other gauge as well. You don't have to work in unitary gauge. This is just a choice that you see explicitly that the mu becomes massive. Okay, if you work in other gauge, of course, it should be the same. Okay. And then you are going to have the mass term for the Higgs. Yeah. Okay. And then here, yeah, this generate MH square the mass term for the Higgs. Okay. So what I wanted to say is that before and after symmetry breaking, let's say that this is before symmetry breaking, and then this is after symmetry breaking. In the local U1 case, what you have is that before you break the symmetry, you have the complex scalar field and the mu. Okay, and this complex scalar field has 2 degrees of freedom, real and imaginary, and then plus mu. Before you break symmetry, it has U1. It has a gauge invariance, so it should be 2 for mu. But after you break the symmetry, what you get at the end is that you get the massive mu, massive vector field, which has 3 degrees of freedom, plus the Higgs field here, H. Okay. So now you see that the number 2 plus 2, 4, no, remains the same before and after you break the symmetries. Okay. So instead of getting, you have the one massive gauge field and then one real scalar field in this case. Yep. Okay. But of course, in this language, when you have the massive gauge field, of course, the gauge invariance, the gauge invariant a mu goes to a mu minus the mu alpha divided by E. This gauge invariant is not in this Lagrangian because of the mass term. Okay, because of the mass term. Right.
Could you explain again why you get 3 degree freedom from setting pi equal to 0 again?
Sure. Because this pi here has a chip symmetry like this, no? Pi goes to pi plus alpha, and now alpha is a function of x, and also we have the gauge invariance of mu, like mu goes to mu minus the mu the alpha, like that. And now, the fact that we have the gauge invariant, we can freely choose alpha that correspond to fixing the gauge. And if you choose alpha to be minus pi,
You mean equal every point?
every point in space-time, this alpha is minus pi, or you promote this guy to be the field or whatever. Yeah, and then that means the new pi, or the pi in the new frame, vanishes. Yeah, and this, when you choose pi like this, when you choose alpha like this, mu becomes massive manifestly. Manifestly, it means that you break this symmetry, and then mu become has a mass term. Okay. I hope this is okay. Right. Okay, I erase this. Right. So now I would like to introduce you another notion of because suppose that we start from this Lagrangian, that you have the massive mu, the massive gauge field, and you have the Higgs like this. Okay. So suppose you start from this Lagrangian, and then you wanted to restore the symmetry. It's a bit confusing now. Okay, let me just write down what we are now. Maybe you're gonna. Okay. Okay. So suppose you start from this kind of a theory that you have a mu and h. And then you have the kinetic term for a mu, and then you have a mass term for the a mu, right? Of course, we know that when the gauge field has a mass term, then it does not obey the gauge symmetry. This symmetry is gone. But then you can do better. You can restore the symmetry by using this Zuckerberg trick. Okay, to restore the gauge symmetry. And now we want to restore the gauge invariance that we break the gauge invariant in the unitary gauge, but we can restore the gauge. We can restore the symmetry by using the Zuckerberg trick, by promoting some gauge parameter to be the field. It's kind of back and forth doing this thing, you know. Yeah. Okay. Let me just finish and then restore the gauge invariance by performing the Zuckerberg trick. Okay. Well, you can start from the Prokop field, whatever, which is a massive vector field as well, Lagrangian. And then to restore the gauge invariant of a mu, you just do the following. So you just take a mu and then introduce another field. Let's say pi field. Oops, shit. Like this. Over E. Yeah. So once you just take this a mu and then you substitute a mu as a mu plus d mu pi and then plug it back here. Plug it back here. And then what you get at the end is the one that we wrote before. Okay. So in this sense, you start from the Prokop field like this, massive gauge field, and then you want to restore the gauge invariance. You do this trick, but then there's nothing free, you know. There's a price to pay. To do this, you have to introduce another massless mode, which is the longitudinal mode here. Before, in this language, a mu has 3 degrees of freedoms, but when you reintroduce pi like this, a mu has 2 degrees of freedoms. Okay, so maybe it's yeah. So when you do this, the mass term becomes simply a mu becomes yeah, the mass term, okay, I can just write down like this. Okay, so the mass term become like this, no? This term, you just substitute a mu as a mu plus d mu pi, like, okay, like so. And then when you have Lagrangian like this, you realize immediately that this Lagrangian has the following invariance, the following symmetry: a mu, d mu minus d mu alpha divided by E, and then pi goes to pi plus alpha. So you go back to the original form that you had before. And when you have the gauge symmetry, a mu now has 2 degrees of freedoms, not 3. No, and then but the price to pay is that you have to have the massless scalar field. So in a sense, you have the 2 transverse mode from these, and then 1 massless scalar field. Yeah, pi. Like, because it has a SHEAP symmetry, so it should be massless. Okay, so this procedure is called the Zuckerberg trick to restore the gauge symmetry. And I hope that when we come to gravity, when we come to diffeomorphism, because we are going to replace this gauge invariant with the diffeomorphism for gravity, and then a mu here plays a role of g mu nu, and then gauge invariant will be replaced by diffeomorphism, and then we do all the same game like this. Okay, I hope. Should we take a break? Let me check.
We have more 10 minutes if you would like.
Let me just write down one more thing and then stop. Yeah. Because I think now there are a lot of informations. I don't want to put more because one can discuss. You can think of what about the mixing between, you know, when you reintroduce the Zuckerberg field pi like this, there is a mixing between d mu pi and a mu. And one could discuss about the decoupling limit between a mu and pi as well. But I leave that later. Okay, maybe it's more. Anyway, so the one last thing I wanted to mention is the when we do cosmology in the next lectures, in next session, we are going to essentially replace the U1 gauge symmetry with diffeomorphism. So, so in this case, for the U1 case, we have local U1. We have the gauge symmetry and the gauge invariance. And when we discuss about gravity, we possibly plus the scalar field. This gauge invariant will be replaced by diffeomorphism. Diffeomorphism. That is like a general coordinate transformation that you have. Okay, and then a mu and a mu will be replaced by g mu nu, in a sense, yeah. And here, yeah, we have passive scalar field, a complex scalar field, and a mu, right? And here we have g mu nu and the scalar field, another one. Okay. And yeah, so we are going to do the same analogy as in the case of the local U1 case with gravity. Okay, and I think probably that. Let me check my note. One last thing. In the case of U1, we have broken U1 down to nothing, no? And then we have one Goldstone boson, right? But in the case of gravity, we start from the 4D diffeomorphism in 4 dimension. If you choose some background of the scalar field here to be time dependence, for example, and that is going to break down to the 3D diffeo. Okay, and this is going to be our symmetry breaking patterns for formulating the EFT of inflation and so on. Okay, that's it. That's it for now. Yeah.
Questions?
Sure. For the massive gauge field, I think if you have this Lagrangian for a mu, then you can write the equation of motion of these. So you're going to have something like this, no? M mu or something like this, mu. And then you can take another derivative, and then you get more constraints. So instead of to start from 4, right, for a mu, 4 components vector, and then you have you minus this a mu, d mu equal to 0, because when you take one more derivative, d nu, and then this anti-symmetric symmetric will about 0, and then you get this d nu a mu equal to 0. So you have another constraint for a mu. So you start from 4 and then minus 1, so you get 3. Okay, and from masses you get 2. Yep, because of the gauge invariance.
Thinking about the Lagrangian.
Yeah. Then we have to. I think you can still use this trick, but it depends on how you couple a mu with other fields. So I have to see how this a mu couple to other field, and then see whether, yeah, it is still safe to use the. But usually yes,
So there's some kind of like the property that we want, so that we can use this kind of trick, and there's some if the coupling is like to actually we cannot use this one, right? So maybe I want to see like what kind of conditions that we.
Well, I don't know. I think when you have, like, suppose that you start from the generalized like Broca theory, the massive gate field theory, or even further, you had mu to some power like square, cube, quartic, and so on, or mu coupled to other field. I think you can always restore this U1 symmetry, but the price to pay is that you have to introduce pi field, and that's it. And suppose mu here coupled with gravity with g mu nu, okay, through the Ricci through the Ricci scalar like this, Ricci tensor, but and then you do this, then you're gonna have a coupling between gravity and pi field. That's it. Yeah, and you have more. Then we can discuss whether it's when it's decouples or when it's when the mixing is very small and so on.
let's start the lecture.
Okay, we'll come back to the first, I don't know, third or fourth section. Anyway, because I lost the track. So far we have discussed just a few theories in Minkowski and like gate field, U1, complex scalar field, and so on. But now we are going to jump to cosmology, where you have both gravity and also the scalar field. Okay, so here we are going to focus mainly on the scalar tensor theories. Okay, and this will be for the scalar tensor theory. Tensor theory. And for this, you have 3 degrees of freedoms, 3 physical degrees of freedoms, 2 for the graviton, for the tensor, and 1 is for the scalar field. Okay, but the fact, since we are going to discuss on inflation or dark energy, I think it's nice to review a bit on the inflation background, but I'm not sure whether in the cosmology already, no? Okay, good. I can skip. So yeah, during inflation, yeah, of course, we know that. So I will neglect. I will omit those like horizon problems and the problem. I take for granted that you guys know this stuff already. So inflation, essentially, is like quasi de Sitter phase. Okay. Quasi. Okay, so in quasi in the sense that the inflation has to stop at some point, but at the first approximation we can use the Sitter metric to describe dynamics of the scalar field or tensor field around this background. Okay, so the Sitter metric in the conformal term is like this. Okay, so it has 10 isometries, fine, and then it has 3 translation, like translational symmetries, and then it has 3 translation, and then 3 spatial rotations. Okay, and another 4 symmetry you have is the scale invariance. Okay, 1 scale invariance, spatial rotation. And then you have scale invariance. Another 3, you have the what they call spatial conformal for this. I will not, but just write down. Okay, if you guys are interested in, it's okay. And you know that during inflation we have the background dynamics of the inflaton that we call phi bar. Okay, and the background of the inflaton is time dependent. It depends on t. Okay, and this guy, we say that the fact that this guy depends on t, then it's going to break time diffeomorphism spontaneously. Okay, so this guy breaks time diff spontaneously. Okay. And I think it's more convenient. Then we are going to write down the EFT based on these symmetry breaking patterns. Okay, so you start from the 4D diffeo, and then you have the non-trivial background for the scalar field, and then this 4D diffeo has been broken down to the 3D diffeo. Okay, so the 4D diffeo is now broken to the 3D diffeo. So the 3D diffeo remains the good symmetries of the EFT. Okay, and thanks to these breaking patterns, then I think it's convenient to introduce the ADM formalism for that, and then we're going to build up the EFT based on the ADM quantities, like the extrinsic curvature, the left function, and the shift vectors. I assume that you have seen ADM formalism, but fine. Fine. It's just the fact that you break you write down in a 3+1 decomposition, because now we have sort of the preferred time direction. It's natural to define the like a normal vector like this. Okay, so you have a hypersurface like this. So you can choose phi bar to be constant. So this is a surface of phi bar equal to constant. So it's a space-like hypersurface. Okay, space-like hypersurface. And then you can build up the normal vector to this hypersurface as the n mu to be minus the mu phi divided by square root. Okay, and this n mu is time-like vector. N mu is time-like vector, and this hypersurface is a space-like hypersurface. Okay, and on this hypersurface you can cook up some geometrical quantities like extrinsic curvature, what we call k mu nu. I know it's like kind of. Let me just write down the ADM formalism. Okay, good. Sorry. Okay, so here is a metric in the ADM form. Okay, so you have this n, which is like a left function, which is a left function. I hope you have seen this before, left function. And then the ni is a chip vector. Chip vector, cheat vector. And the Hij is it's called the induced metric. Okay, and from this form, from this ADM form, you can obtain the inverse metric like G00. This is the 0,0 component of the G mu nu. Okay, which is -1/n squared. Okay, and then there is also GI0. And also there is the inverse of Gij, which is Hij minus divided by n squared. Okay. And now the fact that in our EFT we have this 3D diff invariance, so that means we can write down all the terms in the action that compatible to this symmetry of the EFT, which is the 3D diff field. Okay, right. So let me just so now not only this, you can also compute the extrinsic curvature. Okay, let me just write out it. Okay, like this. The extrinsic curvature. K mu nu. S mu. Okay, so you take a covariant derivative of the vector in mu, and then you project onto the surface. Okay, using this induced metric. Okay, right. So or you can write down Kij as a function of the ADM quantities like this. So. Okay, and the big D here is a covalent derivative defined with the metric Hij, okay, on the 3D surface. Okay, it's a covalent derivative. There are many covalent derivatives, so be careful. It's a covalent derivative of defined by Hij. Okay. So yeah, so now the action that we are going to write down, the EFT action, has to respect the 3D diff field. Okay, so that means it should be the 3D diff covariant quantities. Okay, it has to transform in the covalent manners under the 3D diff field. Okay, so this EFT Lagrangian can be a function of first t, because we break a time diff field, so it can be explicit function of time. Okay, the first thing that you can think of, and also it can be a function of the extrinsic curvature, because these Kij guys here transform covariantly under the 3D diff field. So it's a Kij, or it's a function of G00. Okay, G00 guide here. Okay, and maybe I can show you how this G00 transform. Okay, if you want, yeah, maybe around this here. Okay, I can show you how G00 transform. Okay. So yeah, if you want G00 in a new frame, like in the tilde frame, transform in this way. So you have T tilde dx mu, and then G mu nu. Okay, this is how the metric transform, no, under the coding transformation, but we are interested in the 00 component of the inverse metric. Okay, and this simply becomes the delta 0 mu G mu nu, and this is equal to G00. Okay, so you are saying that under the 3D diff transformation, this G00 is a nice object in the EFT, because it transforms, is like a scalar under the 3D diff field in that sense. Okay, scalar under the 3D diff field. That's why this G00 is one of the building blocks of the EFT. Okay, so it's one of the building blocks of the EFT. So not only this G00, also this Lagrangian can be a function of the curvature, like the 3D curvature that you defined on the hypersurface there. Okay, so it could be a function of the 3D Ricci, okay, that you define on the surface there, and then it could be a function of the covalent derivative and so on. Okay. Of course, in this EFT, you can write down terms that are invariant under the 4D diff, like Ricci and 4D Ricci and the Ricci square and so on. But we don't care about that. Okay, we care about this the 3D quantities. Okay.
So that's covalent diff. It's 4D or
4D. Okay. Let me just write down this the general form of the EFT of inflation, and then I will go on. Okay. Okay. The general form of the EFT is the following. General form of the EFT. By the way, now we are more like a bottom-up approach. Okay, since we don't know about UV completion of this, so we just kind of building things from the bottom and then going up. But we are in the so-called unitary case. Okay, because you remember that we have chosen phi bar to be a constant or to be a function of time, or we choose the background of the scalar field to be the time coordinates. So yeah, we are in a unitary case. In a sense, we set pi to 0. And or we choose or we identify the phi bar as our time coordinates. Okay, so as T. Once you do this, you basically in the unitary case. You are in the unitary case, and we can write down the EFT action is like this. And then this Lagrangian, as I said, can be a function of the 4D curvature, because the 4D curvature is nice because it's invariant under the 4D diff. So you can include these 4D things, 4D quantity into the EFT, no problem. Okay. And then for the 3D quantity like G00 and also the extrinsic curvature and the 3D curvature, you can also include that in the Lagrangian. Okay. K mu nu, one derivative, and also it can be a function of time explicitly. Okay. All right. Now we have this generic form of the EFT, and then the thing is, this is not in how to say. You have to do something about this form. You have to expand around. You have to, because this is not practical. Then we have another form that's more practical, that you can use that to do some calculation. Okay, but before that, we are going to define the perturbations, because this EFT is an EFT of perturbations. Okay, so it's EFT of perturbation or cosmological perturbation. Cosmological perturbation. In the sense that once you write down the action for this perturbation, you can basically use that action to compute the observables without passing through the background dynamics, because it had been fixed before by the background FRW and so on, or Sorolo inflation, whatever. Okay, so let me just define the perturbation. Okay, define this delta G00, which is the perturbation of G00. As G00 minus G bar 00. But G bar 00 for FRW is minus 1. Okay, so it's minus 1 for FRW. So this guy is simply G00 plus 1. And you can do the same for the K mu nu, for the extrinsic curvature. K bar mu nu, and then the background extrinsic curvature is the proportional to Hubble, because Hubble is the only scale in your FRW in a sense. So this is just the H delta mu nu. Okay, you can take your FRW metric, okay, and compute the extrinsic curvature for that. You're gonna get this. Okay, H is the A dots divided by A. Okay, good. And of course, delta K, you can take a trace for this by contracting with H mu nu or G mu nu, whatever. And then you get K minus 3H. Okay. So right now we are going to expand that EFT action around the background five bar, and then expand order by order in these perturbations. Okay, we're going to expand that Lagrangian. Okay. 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 So expanding around the cosmological background. Expanding around cosmological background. What you have is the following. Let me finish writing and then I explain later. Okay, because it's kind of long. Okay, here we go. So the first term you have the usual Einstein-Hilbert action, the usual Einstein-Hilbert term. Okay, Okay, this term is a 4D diff invariant, so we keep it like it is, okay. And the next term you have lambda as a function of t, okay. And this is allowed in our EFT because we break time diff, so the explicit function of t is allowed to add, okay. And then you have a linear term in G00, okay, the linear term in G00. And then you have the high order terms in perturbations in this guy, in delta G00, in delta K mu nu, and so on. Okay. So for example, you could have terms like this. M2 to the 4 delta G00 squared plus and so on. Okay, and also you could have the term with the delta K mu nu. Okay, something like this. You can see that the coefficient of the EFTs, like if M2, M3, M1 bar can be a function of time, okay? Because we break a time diff, so they are allowed to be a function of t.
So lambda is just arbitrary function.
Arbitrary function. We have not fixed anything yet, so this is completely general around the cosmological background. Yeah.
It's a kind of coefficient in when you expand.
Multiple expansion, exactly. So if you think of that, exactly, thanks for the help. This is kind of like doing the multiple expansion in the case of electrostatic. Yeah, this lambda more like a Q charge and then so on. More, but not exactly, but the analogy that thing, but not exactly that, not exactly multiple, but yes. And in principle, you can add more terms like delta K 00, sorry, delta K squared, whatever. And so on, okay. Right. So let me comment on the first three terms first, okay. So the first three terms here is the so-called the tadpole terms. This is the tadpole terms. And because these three terms, only these three terms completely fix the background dynamics, okay, by using the tadpole cancellation condition. Tadpole terms completely fix the background dynamics. What I mean is that only these two functions, lambda and c, is enough to fix the background dynamics of inflation. Nothing else. Just two functions. Okay. Fix the background dynamics. Okay, so let me show you how these two guys fix the background of inflation. Okay. So if you vary this action with respect to G mu nu, you are going to get the Einstein equation, right? Okay, and on the left-hand side, you get the Einstein tensor, and on the right-hand side, you get the T mu nu. Okay, imagine that you do the variation with respect to G mu nu, then you get, try to do this at home or exercise. Vary this with respect to G mu nu and see what you get. But remember that we also have square root minus T in front, so don't forget about that. Okay, so let me just write down the background equations. Okay, that completely fix the background dynamics of inflation. Okay, so yeah, if you compute T mu nu, which is the trace energy momentum tensor, using the usual formula you know in love. Yes. Okay, you plug, you use the EFT form there and plug it here. You vary to G mu nu. The first term, the Einstein-Hilbert action, gives you Einstein tensor, fine. And then the second term give you this one, C minus lambda G mu nu plus C delta mu 0, delta nu 0. Okay. So basically, the lambda term, guys, here, when you vary this with respect to g mu nu, it's only hit on this square root minus g. That's why it's proportional to g mu nu. But for C, the second term here, this G00, you have to value with respect to G mu nu. That's why you get the delta 0 mu here. Okay, final. And then you just write down the Einstein equation, like Hubble, the Friedmann equation. You get the following. Okay, this is the first Friedmann equation, and the second one is this. Minus. Okay. So now you see that fixing lambda and c, this function of time, you completely fix the background dynamics, which is described by Hubble. Or in other words, if you fix a Hubble, if I give you some background, some cosmological background with some Hubble as a function of t, then you can determine what lambda and c are by fixing this. Okay, so that means that the input is a background dynamics or the FRW metric. If I fix the Hubble, then I completely fix the lambda and c. Okay. Then I go on to study perturbations starting from these terms, delta G00 square, cube, and so on. And these start at the second order in perturbations. Okay, so there is no background dynamics here. The background is fixed by these three terms. That's it. Okay, you can recognize that this C plus lambda is more like for the skeleton tensor case is phi dot square plus the potential. In the case of canonical single field, but you can have more general case as well. Okay. Yeah, if you use these two equations, you can fix lambda to be the following. Here, let me just write out here. Yeah, you have these two equations. You can write down C lambda in terms of Hubble and its derivative like this. And lambda is okay. So given Hubble and H dot, you can determine lambda and C. That's right. And of course, if you impose a null energy condition, that means Hubble should be negative, H dot should be negative for null energy condition. H dot should be negative because rho plus P is positive, no? Yep. That means C should be negative, positive. Yeah, C should be positive when you impose a null energy condition. Yep. Anyway, it's just the side, the thing that you should, the note, the side note.
But it also means that lambda and c, they are dependent.
They are dependent, I mean, to each other or?
Yeah, to each other.
Right, right.
If I substitute, I replace H dot with, I can replace H dot with the C.
Mm-hmm. Yeah, see here.
And write lambda as some, something instead of C.
Yeah. Yeah, that's right. Oh, like this equation. Yeah. Yes. Okay. Let me show you the example, the simple example that how to understand this EFT in term from the language of the covalent theory, like a single field model or KSN that you have learned in the previous lectures. Okay. So in that case, okay, fine. Okay, let me just give you examples how to kind of match this EFT with the covalent theories. Okay, so the first example is the canonical single field. Canonical single field model. Okay, so in this case, of course, we all know that S is just this canonical single field and minimally coupled with gravity. Okay. Okay, so you just simply have the Einstein-Hilbert term and the kinetic term for the scale and the potential term. Okay, that's it. Canonical single field. And then from these covalent theories, canonical single field, we are going to match with our lambda and c, the EFT parameters. Okay, so the idea is that you start from this theory and then you go to unitary gauge. Okay, so we are going to choose phi to be phi bar. Okay, and what happened is that when you choose phi to be phi bar, this kinetic term, the mu phi squared is G00 phi bar dot square, like this, no? Only this. Okay, so this means you work in the unitary gauge. I remind you that in unitary gauge, we have only the 3D diffusion. Okay. Keep in mind that we can still have a choice, have the freedom of reinstalling the gauge, the 4D diffusion, but I will talk about it later. Okay. Anyway, and then this potential V of phi, since phi becomes phi bar as a function of t, right? This simply becomes a function of t only. That's it. No? All right, and now this action becomes this way. The Einstein-Hilbert action just remain the same, and you don't touch this part. And then this becomes simply 1/2 G00 phi dot phi bar dot squared. I hope you see, and then minus V of t. Okay. Change the class. But thank you. Okay. Now you can match this form of the action with the lambda and c that we had before, the form of the EFT. So you match this with this form, d4x. Yeah. Minus lambda and the minus c G00. And by doing this, you can determine what lambda and c is in terms of the canonical single field like this. Okay. So in this sense, lambda is simply just the potential, just V of t. And then c is phi 0 dot square divided by 2. Okay. This is what we call a dictionary of the EFT. Dictionary of the EFT. Dictionary in the sense that once you know the covariant form or covalent theories, you can map this into the EFT language, into the EFT parameters, C and lambda like this. But in general, you don't have to do this matching. It's just when you specify your theory, your covalent theories. But in general, when you do the practical calculation, like 2-point function, n-point function, and so on, you can just take your our EFT action and do the computation without even specifying the covalent theory like this. Okay, this just to show you that this C and lambda already how to say enough to describe all the dynamics in this single field case. Okay, just C and lambda, two parameters. Yep. Yeah, you can have you still have the Kaigon equation for the phi bar double dot and plus 3h phi bar dot and so on. But okay, that's another. Right. Another example is the one of the cases. I think maybe it's worth to ลบครับลบมันเลยครับ the one case. Okay, so let me write down the k essence action. K essence action. So you have like the action like this. Okay, and then plus the term that depends on both phi and x. Phi and x. So this p is a general function of x and phi. Okay, and x here is a kinetic term of the scalar field. Okay, and once you go to unitary case, no, you go to unitary case. Unitary case by choosing phi to be a phi bar, okay, to be phi bar of t, then this p of x of and phi becomes simply just a function of g00 phi bar dot the square phi. Okay, let me remind you that in the case of the gate field U1 that we did abelian Higgs, when we choose unitary gauge, the scalar field has been eaten by the gate field, right? And the gate field becomes massive. In this case, the analogy is that the metric eats the scalar field. Okay, let me just write just to give you keep in mind. Keep in mind that in unitary gauge, the scalar field has been eaten by the metric. So now the scalar degree of freedom is inside the metric. Okay. By G mu nu. And in G mu nu, usually you have 10 degree of 10 components, no? If you don't, And then if you include this, it's going to be 11. But this is after you fix the gauge and so on. We know that in GR we have the gauge freedom to choose. Not all these 10 is going to be your physical degree of freedom, but anyway. But yeah, what I want to say is that this phi in unitary gauge is inside, the scalar degree of freedom is inside the G mu nu. Okay. In other words, it's inside this guy. G00 here. Okay. Of course, then when you have these, then you can totally expand around around 1 basically, because the G00 is just a G00 plus 1. So you can expand this function P of G00 as a function of delta G00 like this. Okay. Let me expand it. Yeah, you simply have G00 just 1. And then plus px and G00, and then first order in delta G00, and then you can have high order like pxx, maybe 1/2, and then delta G00 squared, something like this, and so on. Okay, let's expand this. And then after you expand, you expand this around in term delta G00, you can do the matching between this p and the derivative of p in terms of the EFT parameters. Okay, so remember that in the EFT we had terms like delta G00 squared, delta G00 cube, and so on. By doing this matching, we can determine the EFT parameters, now including the high order terms like delta G00 squared, delta G00 to the n, and so on, cube. Yeah, so in this sense, yeah, we can determine the parameter m, the function of 2n dn. And this evaluated on the background on phi bar. And then C is given by minus phi bar square dot and P of x bar. Px bar is the P you take derivative and then you evaluate on the background. Okay, and then lambda is minus p bar minus phi bar dot squared p of x bar. Okay, nice. Let me remind you that we have this kind of action. In the EFT language, lambda c g00, and then minus 1/2 delta g00 squared and 1/3 factorial delta g00 cube and so on. Okay, so you can do the matching between these EFT parameters and the one that you know from the KSM theories. Okay. Okay. And now, yeah, maybe 1 or 2 comments. I think it's nice to do some comment that when P of x is 0, when P of x is 0, lambda is just a constant. So this plays a role of the cosmological constant. Yep. When P of x is 0, this lambda is essentially cosmological constant. So you have basically the De Sitter solution for this cosmological constant. Yep. What else? And yeah, well, if you compute the pressure and rho and energy density, the pressure, this pressure, okay, is simply equal to the this p bar. That's why we call P, because P is there, it's the pressure itself. Yeah, and rho is essentially minus p bar minus 2 phi bar dot p of x bar. Okay. And you have any questions over before I go to perturbations? Or we take a break? Yeah, maybe yes. Maybe, yeah. I think the maybe the next lecture will be to how to restore the 4D diffeomorphism. So when you write down the EFT in this unitary case, you don't have the full 4D diff invariance. But then in some cases, it depends on your situation. We want to restore the 4D diffeomorphism invariance by using the Zuckerberg trick, and for that we have to introduce the scalar field fluctuation. Okay, and for the next lecture, yeah, I think that's okay for now. Otherwise, yes, yeah. In this case, the vacuum of this case will be this time-dependent scalar field, like the dynamics of the inflaton itself. So it's kind of a time-dependent background. So in that case, it's a constant vacuum, no? And in this case,
like global background, right?
yeah. So in this case, yeah, this guy is our vacuum, phi bar. Yeah, it's a kind of everywhere in space and time.
Have the same.
Well, same everywhere. Of course, it's homogeneous. Yeah, but not in time. Yeah.
Any more questions? Okay, if no, please, and Bishop is okay.
Hello ผมปิดเสียงอันนี้ได้ไหมปิดเสียงแต่มันจะไม่มีเสียงเพลง so the next session we have the quiz again yeah and it's something like summarize the morning to last session so it's quite some question is quite very new yeah very new and challenging yeah very new because nickname of our lecturer is new yeah โอเค ใช่ มันอยู่ในไร
Sorry. Yeah, the next one. Yeah, the correct is egg, right? This one is quite. It's something like this. Boson has mass something like this and get a longitudinal polarization. Yeah. Yeah. I don't know. Yeah, could if I explain a little bit for just a short time. Short.
Okay. Shall I start?
Please.
Okay. Okay. This is probably the last lectures of my talk. So so the last one. Well, actually, we will be able to touch upon the dark energy or black holes since. But okay, I mentioned a bit about that. But as I promised, we are going to see how you perform the Zuckerberg trick, okay, to restore the 4D diffeomorphism from the from the EFT action in unitary case. Okay. So yeah, when you choose the unitary case, you have to be when you do this transformation T to T. I think it's one of the quiz that you just did, no? T plus psi 0, and psi 0 here is a gauge transformation for the translation like this. And so when you do the transformation of delta phi, which is the perturbation of the scalar field. Okay, so you have phi bar T plus delta phi, and this delta phi here transforms as delta phi minus phi 0 bar dot psi 0, and to be able to choose unitary gauge, you have to set psi 0 to be delta phi divided by phi bar dot. So now you see that the fact that you have this phi 0 dot in the denominators, so that means this guy has to be non-vanishing, or even better, in during inflation, this guy is a monotonic function in T. So, okay. So otherwise, when this phi 0 dot vanishes, for example, then this choice of the gauge becomes ill-defined. Okay. So this has to be non-vanishing. Oh yeah. Anyway, so this one comment, and then of course when we write down the EFT action in unitary case, we don't have the full 4D diffeo, but then there is an option that we could restore the gauge, the full 4D diff, by performing the Zuckerberg trick. Okay. 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 So in this case, yeah, we can perform the Zuckerberg trick for, yeah. Let me just choose the two terms in the EFT that we just saw. Okay, these two terms that describe the background dynamics and correspond to the single field, the canonical single field models. Okay, and so in this case, you perform the Zuckerberg trick. Okay, and that means you send T into T plus pi. Okay, and this in the same sense as when you send a mu into a mu plus d mu pi, in that sense. Okay, so you substitute this back into this action. Okay, and what happened is that this G00 will become something like this. Dx d mu nu. Okay, and then this just G00 plus 2 G0 mu d mu pi plus okay. So now you see that when you perform the Zuckerberg trick for G00 here, then this guy is going to contain the scalar fluctuation pi here. Okay, right. So now you can imagine that this term C times G00 in terms of the pi language, it contains the kinetic term for pi. Okay, this is more like a kinetic term for pi. Pi is your inflaton fluctuation in sense, yeah. And actually pi and delta phi are related through some sort of, pi is like delta phi divided by phi 0 dot. Okay, pi here has a dimension of -1, อะไร in energy because it's it's t, and here this one minus one. Anyway, so you can do the same trick to other quantities like k mu nu and also those ADM quantities. Okay, so basically this action of the EFT becomes something like this. Let me erase this. Okay. Cap. Oops. So you start from the EFT action in the utility gauge, and then you perform the Zuckerberg trick. Okay, T go to T plus pi. Then what you get is, what you obtain is the following. So you have square root, and notice that this term d4x square root minus t is already invariant under the 4D diff, so you don't get pi from here. Okay, and also this term Einstein-Hilbert term here is already 4D diff. You don't get anything from here. I mean, you don't get pi from the Ricci, from the 4D Ricci. Okay. So there's no pi here. Eh? And then in lambda you get t plus pi. Okay, and then in C there you get C t plus pi, and then for G00 you have those terms. G00 plus 2G mu d mu pi plus G mu nu. Yep, that's it. Okay, and if you expand this function lambda and c, you are going to get like polynomial terms in pi. Okay, for example, if you expand this, suppose you are in the small field limit, but if you are in the large field limit, you cannot do this. And another story, you have lambda like this, dot pi, and then the tower of pi. Okay, like 1/2 double dot pi square, and so on. So you get some sort of the potential in pi, something like this. But usually during inflation, this lambda dot or lambda double dot or c dot, and these things are suppressed by the Sororo parameters. So normally we are going to take this as 0. So lambda and c, they vary slowly with t. So we sort of neglect this term. And once you neglect this polynomials term in pi, then pi has a SHEAP symmetry in this sense. Okay, so when neglecting all these polynomial terms, you're gonna have the SHEAP symmetry in pi like this. Okay, so sorry, neglecting pi to the n, so you are going to have a pi plus c SHEAP symmetry in a sense. Right, and if you want in this, when you write down the action in this way, you have recovered the 4D diff morphisms. Okay, you have recovered 4D diff. So when you perform the time diff like this, okay, t plus and then pi goes to pi minus like this. Yeah, this action is invariant under this transformation. Okay. You can check. It remains invariant. Okay. เดี๋ยวครับลบเลยครับใช่ครับ Okay. And for other things like ADM quantities like left function and SHEAP vector, let me just write that up to second order in pi. Okay. Okay. Yeah, so basically all of those the ADM formalism get contribution from pi. Yeah, when we do the t goes to t plus pi. Okay. And also ni. Plus order 3. And also the induced metric. And once you know all this, how NI Hij transforms, you can use this formula to obtain the Zuckerberg trick of the Kij of the eccentric curvature. Okay, because Kij is defined in terms of this left function, shift vector, and the Hij. Okay, and notice that the derivative here, dt or d0, is also transformed under this t goes to t plus pi. Okay, so t goes to t minus pi 0. And pi dot squared, I think, yeah. And d0 plus high order terms. And di also get contributions from pi. Yes. So things become messy. As usual. As usual. But this is life. This is life. Yes. Okay. So yeah. So all these formula you can reconstruct you can to get the Zuckerberg trick of Kij. Okay. Because Kij is simply 1 over 2n Hij dot, right? Minus din j minus dj in I. Okay, you use this and then plug it here, but be careful about this covalent derivative. There's also a Christoffel symbol of Hij here, and perhaps you have to know how this guy transforms. And this guy, of course, is defined in terms of Hij here, and you know the formula of that. Okay. Right, and yeah, let me just give you the how. Maybe it's nice to, yeah. So yeah, and well, wait. Let me just complete. Yeah, so this is the formula of the Zuckerberg trick of delta k, and delta k, I remind you that is k minus 3h on the FRW background. And once you do this transformation, t goes to t plus pi, you get this the formula up to, yeah, this is first order in pi. Okay, but notice that on the FRW metric, the left function and the shift vector essentially is of order of perturbations. Remember, because the FRW metric is like this, no? You don't have the off diagonal terms, right? Yeah. So when you have this ni is already first order in perturbation, and n here actually when we do cosmological perturbation, we do like a 1 plus some like a Newtonian potential or 2 phi if you use a Newtonian gauge. Yeah. So we come to that. Oh shit. นิดหนึ่งตรงนี้ก็ได้ตรงนี้ก็ได้ครับไม่เป็นไรผมลงกันนะครับ Okay, so now what we are going to do, how many minutes do I have? Like half an hour? Half an hour? Okay, good. In this half an hour, I'm going to do the decoupling limit of of inflation. In the sense that we are going to fix gravity, we are going to fix the background metric to be FRW essentially, or the theta if you want, during inflation. And then we are going to study the dynamics of pi, of the inflaton fluctuation using the EFT. Okay. So in this sense, once you fix the background metric, you don't have to solve the constraint equation. That simplifies your life a lot. Okay, so here we are going to study the decoupling limit of decoupling limit action during inflation. So it means that the background metric has been is fixed by, say, the theta metric. Okay, T mu nu is fixed. So then you don't have metric perturbations that simplify your life. Okay, you don't have the Newtonian potential or whatever. Yeah, fixed to be say the theta background. Okay. Actually, when you go to decoupling limit, it means gravity and scalar decoupled. And in this limit, what we think of is when we send M Planck to infinity, in a sense, okay? And or you send epsilon to 0. Epsilon is a Sorolo parameter defined by minus h dot divided by h squared. Okay. Once you fix the combination M Planck squared and the Hubble dot remains constant. Okay, so we are in this limit. So we basically set epsilon to 0, and when we set epsilon to 0, it means that those when you solve the constraint equation for the left and the SHEAP vector, since they are proportional to epsilon, so basically you don't have to solve them. So you just fix them to be the one of the inflation, the one of the FRW. So basically ds is minus dt squared plus a. Okay, you just forget about gravity. Basically, you forget about left function, or well, you take a left to be 1, basically, or minus 1 here, and then you forget about the SHEAP vector. And then Hij is just a square like this. Okay, and now we are going to write down the action for pi field only. Okay, so we and see what comes out. Okay. Okay. So in this case, yeah, suppose you take this action, you do the Zuckerberg trick, and then you have the action for pi. So basically, this when you see this T00 in decoupling limit, you substitute this T00 to be minus 1. Okay, because you fix gravity, you fix the background metric. And when you see this T0 mu is 0. Yeah. And then this is just 1 over scale factor, and then delta mu nu. Well, no, caso che. I do this. I do this. Boop, boop, boop. Okay.
The second
Thank you. Yes, thank you. This is 2 pi dot minus, and then 0 I is 0. Yeah, sorry, I was too quick. Anyways, and then you can have more terms like delta G00 squared and delta G00 cube and so on. So from the delta G00 squared, what you have in this decoupling limit is that m2 to the 4th, and then let me look at the thing. And this is after I substitute the background, the FRW background, okay. So this term is coming from delta G00 squared. Okay. This term from terms like these. After you perform the Zuckerberg trick of delta G00, and then you fix the background metric to be FRW there, and then you get this the term for pi only. Okay, and now you see that you have the cubic interaction of pi, the self interaction of pi here. Okay, and then you can think that when you compute the so-called bispectrum or the 3-point function of the scalar field here of pi, then that thing is going to be proportional to this m2 to the 4th. Okay, but now before going to the non-Gaussianities, let me just discuss the quadratic order in pi first. Okay, because here it has some non-trivial sound speed. As you can see that from this CG00 you have the usual kinetic term for pi like this on the FRW background, but this the G00 square term generates this pi dot square term. Okay, with the coefficient m2. So now you can define the non-trivial sound speed for this for the pi field. Okay. Okay, so this term is coming from CG00. Okay, so it just C is m minus m Planck square h dot, right? So you just substitute that, and then from m2 to the 4th term you have the following. You have this plus m2 to the 4 pi dot square. Yeah, two, sorry. Okay, and then you can define these as something like this: m Planck square h dot divided by cs squared. Where the sound speed cs is defined by the following. Okay, then now you have the formula for CS in terms of the EFT parameters like this. Okay, and so now you notice that when you send M2 to 0, you recover CS equal to 1, right? You said when you send M2 to 0, for some reason, you recover CS to 1. Okay, in this sense, you recover Lorentz invariance because in the sense that the sound speed, the time and the spatial derivative are in the same footing. Okay, because this m2 to the 4th term here breaks Lorentz symmetry, actually breaks the Lorentz boost because you don't have it's just a pi dot squared. Okay. So now you recover in this limit, you recover Lorentz invariance. Okay, but there's another limit where suppose that h dot exactly equal to 0 when you send h dot to 0, exactly equal to 0, not just go to 0 like this. When h dot equal to 0, then CS go to 0. Of course, go to 0. In this limit, you are in the so-called ghost condensate limit. Condensate limit, and it has some problem. That is, it leads to the strong coupling problem that I will maybe discuss later. Okay, this leads to the strong coupling problem, but in the EFT framework, this is not well. One has to include other operators in the EFT in order to solve this strong coupling problem. Because for now we just consider delta G00 squared, and it could be that when this happens, other terms in the EFT become play important role. Okay. Okay. Well, we'll see later. Yeah. Yep. Okay. Okay. Now, so since we have this quadratic action for pi, which is our Goldstone-Boson field, and during inflation, usually we compute the if you recall, we compute the 2-point function of curvature perturbation. That is our physical observables that we saw in the CMB. Like we can map this quantity to the CMB observations. I don't know. There's a map between curvature perturbation and pi field here. Okay, so let me just quickly mention that what is curvature perturbation. So usually when we do the cosmological perturbation, we can introduce the curvature perturbation through the Hij it sits in front of the scale factor squared. Okay, introduce the curvature perturbation, and in this case, Hij is simply e to the 2 theta. And theta here is a curvature perturbation and times the scale factor square and delta Ij. Okay. And by doing the gauge transformation, you can connect this pi there, the Goldstone boson, and this curvature perturbation using this relation. Okay. So maybe this is a bit quick, but you have a relation between theta that should be frozen outside horizon, okay, and the pi field here, and the Goldstone boson. Okay, theta here doesn't have dimension because it appears as an exponential in the metric, in the spatial metric here, and pi has dimension -1, so h pi doesn't have dimension. Okay, so this guy is the one that is frozen outside horizon in the single field model. Okay. When I said outside horizon, it means that the k, the momentum of that mode is very low, less than ah. Okay, or large scale. Okay, inside horizon means k is larger than ah. Right, and then yeah. So from this quadratic action for pi in terms of CS, you can simply calculate the 2-point function of pi, right? And it depends on CS, and then you translate this 2-point function of pi into the 2-point function of zeta, and then you can define those like spectral index and the amplitude of power spectrum and so on. Okay. Now, yeah, this is maybe a bit quick, but since it's the last lecture, so I can do anything I want. This is the last lecture. This is the last lecture. Okay, so so basically the way to compute the 2-point function of pi during inflation, you have to find the classical solution for pi on the FRW background, and let me just write down the solution for that, and then I go on. Okay, so you find the classical solution for pi in the Fourier space. So you take the quadratic action for pi, and then you do the Fourier transform. Okay. I shouldn't relate this, but anyway, yeah. And then you solve this the classical part for pi, okay. And the equation of motion of pi from that Lagrangian is the following. Yes. Notice that here we are in the cosmic term, okay? So you can use the cosmic term or conformal term, whatever you like. But we use this the Fourier transform like this. Okay. Okay, and T. Okay, so we just Fourier transform in space because we are not allowed to do the Fourier transform in T because we break T. So we just plug this into the quadratic action that I just showed you, and then you write the equation of motion of pi in Fourier space, and then you have this equation of motion. Then you solve this, and it's just like this. So basically, okay. Minus. Sorry for my notation, but now I change to conformal time. Yeah, I got such a. Okay, this e to the I k eta. And eta here during inflation runs from the minus infinity to 0. Well, to some late times limit. Let's say eta c. But then usually we take this eta c limit to 0 at the end. Okay. This solution corresponds to the plane wave solution in Minkowski. When k eta is very large, like k eta goes to infinity, then basically you go back to the Minkowski plane wave. Plane wave solution in Minkowski. Okay, so basically when you send k eta to be very large, like super sub horizon, then essentially you go back to the flat space, and then you recover all the the time translation. Then you have the conservation of energy and so on. Okay, so yeah, basically this is kind of to make sure that the choice of the vacuum is okay. Okay, and then once you use this classical solution for pi, and then you can compute the 2-point function of pi. Okay. And the 2-point function of pi is given by this. Oh, sorry. Once you have pi here, then you can use this formula to get the curvature perturbation. Okay, and then at the end we compute the 2-point function of zeta of the curvature perturbation, k1, k2. Okay, and this is 2 pi cube delta 3 k1 plus k2. Actually, this delta function in k space essentially coming from the fact that we have the homogeneity. Okay, so we have the translational symmetry, a spatial translation. Spatial translational symmetry. And then you're going to have the amplitude of this, let's say p theta. Okay, and p theta here is only a function of the magnitude of k because of the rotational symmetry. Okay, and p theta here is given by the following. Let's see how it's okay, so now you have this formula for the amplitude of the power spectrum, and the first piece, yeah, you have this Hubble divided by M Planck, and also there is a Sororo parameter here in the denominators. Okay, and the fact that you have CS here, that means this P guys runs with energy, runs with K, because this C here in principle depends on K. Okay, so you can write down this as 1 over K cube plus NS, something like that. Okay. Yeah, so let me. So this is more like the running of the power spectrum. Okay. So this define how the amplitude runs with K, D and And then yeah, so it depends on how CS changes with K, something like that. Well, but now you see that in the small CS limit, you can also enhance the power spectrum like P theta. Yeah, and also if you, for example, if you break Sororo, like if you go to, for example, like ultra Sororo models where the epsilon can be large. Well, sorry, no, sorry, I take it back. In that model, eta can be large, but epsilon decreases exponentially. In this case, you could also enhance the amplitude of power spectrum, and you generate primordial black hole and so on. But we don't discuss about that. So what I wanted to say is that, yeah, another thing, the fact that you have the running of P theta, the amplitude of a power spectrum, it means that you break some of the de Sitter isometries, like the scale invariance. Okay, so this the spectral index. Okay, and this tells you how much you are far away from the de Sitter the scale invariance. Okay, so you to break scale invariant, but you break softly because it's proportional to say epsilon and so on. So it's not that much. It's not like a hard breaking, but it's a soft breaking. Because we know from observation that NS should be close to NS minus 1 should be close to 1 or something. I don't remember. Yeah. Right. And if you have exactly 1 over k cube, you have the exact scale invariant of the power spectrum. Okay. By scale invariant, I mean when you perform the this scaling transformation x to lambda x, where lambda is any number you can and eta to lambda eta, and the full action should be invariant under this transformation. So this is what I mean by scale invariant. And the Sitter metric is it has this scaling invariance. Okay, because ds square. So you see that when you rescale eta here with lambda eta and x here with lambda x, and this lambda in the numerator cancel, so that means the Sitter also has the scale invariance. And the observables you computed at the end should follow the symmetry of the de Sitter in this approximation, in this decoupling limit. So we're back to the decoupling limit. So you should respect the de Sitter isometries. Okay. Yeah, but now we break a bit by this CS. Yeah. Now.
Side would be defined as something like horizon crossing something.
Yeah, exactly. So yeah, skip that. So this the amplitude usually we compute it at the crossing of the horizon. Yeah, when the mode exceeds the horizon. Yeah. When k is of order ah. Yeah, I didn't mention this. Right. Now, should I stop or should I? Should I stop?
Do you have something?
You have something more to say?
It's about.
Can you talk a bit about how we get link this a little bit.
Sure. Yeah. For example, in this model, in this M2 to the 4 that I just deleted, it contains 3-point function. It contains cubic interactions like pi dot cube or pi dot di pi squared. Okay, so in this M4, M2 to the 4, it contains things like pi dot cube and then pi dot di pi squared. So from this interaction, you can go on and compute the 3-point function of pi, and then you can translate this into the non-Gaussianity of a curvature perturbation. Okay, so we like this curvature perturbation because it has a direct link to the temperature fluctuation during the CMB, on the CMB. Okay. This guy freezes.
Something like skewness,
Yes.
something like that.
Yes, exactly. So this corresponds, yeah, exactly. So if you write down the distribution function of pi field here, then it's going to have something like this. So suppose you write out the PDF, probability distribution function of theta. Exactly. So what you have is you have the zero order terms like this. Sorry, the leading order term is coming from the Gaussian. Okay, and yeah, if you have the free filter, it's just like this. It's Gaussian PDF, but then you could have like these, FNL and GNL. Kurtosis, exactly, kurtosis, and so on. Yeah, and these are corrections due to the nonlinear interactions like pi dot cube, pi dot di pi squared, and this pi dot to the 4, and so on. So it gives correction to the FNL. And in principle, so far we have not detected primordial non-Gaussianities yet. We just only put the bar on FNL, but it's really large. FNL, it depends on what shape you have, because when we talk about the 3-point function, it depends on K1, K2, and K3. Okay, so there are essentially 2 shapes. One is the so-called equilateral, when all the K's are compatible, and the other is some kind of orthogonal shape. Okay, so from Planck data, I think the equilateral, I think it should be less than 100. But this doesn't mean much because the bound is still large, so doesn't mean much. And also the way we define FNL is times. Suppose you have this theta, and then you write down the Gaussian theta plus the FNL times the theta Gaussian squared. So you have to multiply by the amplitude of theta Gaussian, which is around 10 to the minus 5. So this FNL around 100, so that means you have very small deviation from Gaussian. This guy is 10 to the minus 5. Square is 10 to the minus 10, and this is 100, so it's 10 to the minus 8. So it's kind of small. So basically you are in the perturbative regime in this sense. But I'll talk about this later. If there is.
Can we have more power of FNL? Now we are not sure that we have some signal from non-Gaussianity or not.
Yeah.
We are not sure.
Yeah, we're not sure. Yeah. Well, the thing is that if you suppose you detect the FNL, the primary non-Gaussianity on the CMB scale, so basically you can root out the single field model, because thanks to the Maurer-Senna, now I think I'm going off the topics. Thanks to the Maurer-Senna calculations, the FNL of the single field model is proportional to epsilon. So it cannot be large. But suppose you find a large non-Gaussianity on the CMB scales, then that means the single field is out. You can find large FNL in the multi-field inflation or other kind of inflation. Yeah. But yeah. I think no, it's okay. No. You want to know about the dark energy? Yeah, let me just comment about dark energy and black holes. For dark energy, it's essentially the same as the one of inflation. You can use phi bar of T. Phi bar of T as to make the 4D diff and so on. But now for dark energy, you have the couplings between gravity, between scalar field here or gravity with matters. Okay, so you have matters around you, okay, because at late times, no. And in this case, you might have to consider the screening mechanism, because it's kind of at late times, we know that it should be consistent with the solar system test and so on for dark energy there. Okay, but for black holes, it's a bit becomes non-trivial for black holes, because when you have a compact object like black holes or neutron stars, it introduces the inhomogeneity of the background, okay? because for inflation and dark energy, the background is isotropic and homogeneous. No, but for black hole, of course, we know black hole is an object. It has some inhomogeneities. And in this case, the EFT formulation becomes a bit non-trivial. You have to impose additional relations to make sure that the symmetry of the EFT, like 3D diff, remains okay, remains good symmetries. And this is what we call the consistency relations. But okay, I think, yeah, thanks a lot. Thank you.
Everyone try, right?